Alright y'all, today we are talking about complex numbers. Let's get into it. So, definition. This is the shortest definition we'll have all semester. I equals the square root of -1. Now, how can we do this? Haven't we been saying all semester that we can't take the square root of a negative number? Well, today we're going to learn how to take the square root of a negative number. This I is what we're going to call an imaginary number. Right? So we can take the square root of a negative, but it's imaginary. We'll see how this unfolds. So, definition. A complex number has the form a plus bi, where a is called the real part, and b is called the imaginary part. A few examples of complex numbers might look like 2 minus 3i, or maybe -5 plus I, or -2i, or even something like 5. So here we have a real part of 2 and an imaginary part of -3. Here we have -5 as our real part and an imaginary part of 1. Here we have a real part of 0, right? And an imaginary part of -2. And here we have a real part of 5 and an imaginary part of 0. So technically 5 is a complex number. So here, the real part is 0, and here, the imaginary part is 0. And these are both complex numbers. How can we describe, but clearly, these are a little bit different than this guy, right? This guy is a number we've seen all the time. We haven't seen any of these guys up until today. So the way we're going to differentiate between these is by saying that these numbers that look like these three are non-real complex numbers. And this guy is what we're going to call a real complex number. We've seen real numbers before, and all of those real numbers are also complex. But there are also non-real complex numbers, and those are the ones that have I. Okay, what can we do with these guys? Well, we can do regular addition and subtraction just like normal. So addition and subtraction of these numbers is actually pretty easy. We just combine the real and imaginary parts separately. Like combining like terms. So for instance, let's combine 2 plus 3i plus 1 minus 5i. So similarly to combining like terms, we want to figure out which terms are alike, right? We have our real parts here, so we have 2 and 1, and we have our imaginary parts 3 and negative 5. So we want to combine 2 plus 1, and then also plus 3i minus 5i. We combine these guys, we get 3. We combine these guys, and we get negative 2i, and that's my answer. 3 minus 2i. Simple as that. Now, what would happen if we were subtracting? Here, again, we're just going to follow our basic algebra rules. We have this negative out front, which means we need to distribute. So let's do that. We have 2 plus 3i. We distribute this negative. We end up with negative 1 plus 5i. We again combine the like terms. So we have 2 minus 1 plus 3i plus 5i. We add these guys, and we end up with 1 plus 8i. All right, why don't y'all try one? Let's say we had something like 4 plus 2i plus negative 1 plus 3i. And also, why don't y'all subtract those as well? So 4 plus 2i minus negative 1 plus 3i. All right, pause the video, see what you get, and I'll talk a little bit about it after. Okay, so if we look at these two, I rearranged so that we had our like terms next to each other. So we have 4 minus 1, so we get 3 for the real part, and then we have 2 plus 3, so we get 5i for the imaginary part. Down here we have to distribute the negative first, so that turns this negative 1 into a positive 1, and this positive 3i into a negative 3i. Then we can rearrange in the same way, and we end up with 5 minus I. Okay, last one I want to look at really super quickly. This is just barely an extension of that. Is this guy. So let's say we were looking at 2 plus 3i minus 2 times 1 plus 5i. All we have to do here is distribute this negative 2, just like we did with this negative, to both parts of this second complex number. Super easy. When we distribute this negative 2 to the 1, we'll end up with negative 2, and when we distribute it to the 5i, we'll end up with negative 2 times 5i is negative 10i. So we have 2 minus 2 for the real part, plus 3i minus 10i, and we end up with 0 minus 7i. This is a perfectly acceptable answer as is, or we can just write it as minus 7i. Okay, that's addition and subtraction. Let's look at multiplication. So, similarly to addition and subtraction, multiplication is really just basic algebra. there's not really too much that's new that we need to kind of add into the process. So let's say we were looking at 2 plus 3i times 1 minus 5i. When I have two factors with two terms, what do I do normally? Usually I would FOIL, right? We can FOIL here as well. So we multiply first terms, which happen to be both of the real terms. So we have 2 times 1, which is 2. Then we have outside, so 2 times negative 5i. That gives me negative 10i. Then inside, 3i times 1, which is 3i. And then our last terms, which are both of the imaginary parts. So we have 3i times negative 5i. So we end up with negative 15i squared. So I want us to think about something really quickly. If I is the square root of negative 1, then what is I squared? Well, it should be the square root of negative 1 squared, but if we square something that we've taken the square root of, what is it? It's just whatever was underneath. So I squared is actually negative 1. What does that mean we can do here? Well, it means I can replace I squared with negative 1. I'm going to do that by drawing an arrow through I squared and writing negative 1, right? The arrow is pointing to what it's going to be. So this is going to be negative 1. If I do that multiplication, then I have 2 minus 10i plus 3i minus 15 times negative 1 gives me positive 15. When I add my like terms together, I have 2 plus 15, which is 17. And then negative 10i plus 3i, which is negative 7i. So my answer here is 17 minus 7i. So all this is foiling. We just FOIL. And replace I squared with negative 1. Why don't you all try this really quickly? Let's say you were given 4 plus 2i and then negative 1 plus 3i. Again, all we have to do is FOIL these out, and then we will get I squared when we multiply these two terms together. And so we replace that I squared with the negative 1, and then we combine everything. So pause the video and see if you can solve this yourself. All right, so I FOILed everything here. We ended up getting positive 6i squared, which became negative 6. We added all that stuff together, combined like terms, and we found negative 10 plus 10i. Let's look at, in the lab manual, these few questions. This is in the section Introduction to Complex Numbers. Let's work through a few of these. So this first one, we've seen this already. I squared is what? Negative 1, right? So we have negative 1 times 3, or just negative 3. This second one, we have 4i times 5i. We can multiply the numbers together, we get 20. And then we have I times I, which gives us I squared. Again, I squared is just negative 1, so we end up with negative 20. Let's say we have I plus 2 times I minus 2. First of all, are these complex numbers? Yeah, they are. But they don't look like the ones that we've seen so far. These guys are not in standard complex form. In standard complex form, the real part comes first and the imaginary part comes second. So in standard complex form, we would have 2 plus I and negative 2 plus I. Let's see what we get here when we multiply this out. So we multiply the first two. The first terms we get I squared. Outside term we get negative 2I. Inside term we get positive 2I. And last terms multiplied together we get negative 4. So, of course, I squared is going to become negative 1. But we have something interesting going on. We have negative 2I plus 2I. If I have a negative number and I add the positive version of it, right, negative 2 plus 2 or negative 5 plus 5, that gives me 0. So this is going to give me 0. These guys are going to cancel. So I'm left with negative 1 minus 4. Negative 1 minus 4 is simply negative 5. This is really interesting, right? Because we started with two complex numbers in both of these cases, and we multiplied together and we ended up with real numbers. This is interesting. Let's see if the same thing happens here. Again, these are not in standard complex form, but that's fine. We can see what happens. So first terms we multiply together, we get 2i squared. Outside we get negative 10i. Inside we get negative 3i. And last but not least, we get positive 15. 2i squared becomes negative 1 times 2, or negative 2. So we have negative 2 plus 15, which is 13, plus negative 10i minus 3i, so minus 13i. All right, last but not least, we've got square root of 3 plus I squared. It might be helpful for us to write this out. So we have square root of 3 plus I times square root of 3 plus I. We need to FOIL as usual, so we have square root of 3 times square root of 3, which is square root of 3 squared. On the outside, we have square root of 3 times I. Typically, we'll write the I first, just so that it's not confusing about whether or not the I is inside the square root. So I plus square root of 3. Inside, we also get I times square root of 3. And then last, we have I times I, or I squared. So a lot of things can simplify here, right? Again, we've talked about this once today already. The square root of something squared is just whatever was on the inside, right? So the square root of 3 squared is just 3. Then we have 2 I square roots of 3. So we can combine those terms, and then I squared is going to become negative 1. So I have 3 minus 1, which is just 2. And then I have 2i times square root of 3, because there's 2 of them. So we have 2i square root of 3. This is the answer. This also is a non-real complex number. Okay, back to our notes. More algebra with this stuff. Manipulating. Roots and radicals. So the big fact that we're going to use here, a whole bunch, we're going to be working a lot with square roots in particular, but this applies to all roots. if I have two numbers, m and n, underneath a square root, then I can rewrite this as the square root of m times the square root of n. So what does that mean? We have a second fact. So if I have the square root of negative n, some number that's negative, then I can use this fact to split these up, right? I can write this as negative 1 times n, right? Any negative number can be written as negative 1 times whatever the number is. Then I can split this up into the square root of negative 1 times the square root of n. And what is the square root of negative 1 equal to? Our nice definition of I. So we have I times the square root of n. So if the square root of negative n is equal to I times the square root of n, we're going to call this process of bringing this I sort of outside using algebra, we're going to call that pulling out an I. And why is this important? Well, another fact. We should always pull out any I's first before we do any other algebra. So for instance, if we had something like the square root of 18, we would want to pull out this negative, right? Remember, negative n is equal to I times the square root of negative n, so this is going to give us I times the square root of 18. And now from here, we're going to want to simplify this square root. How can we do that? Use the factors to our advantage. 18 has a very special factor that we can take advantage of, and that factor is 9. Why is 9 special? Well, 9 is special because it has a square root that's an integer, right? If I split these up, I then have the square root of 9 times the square root of 2. What is the square root of 9? It's 3, right? So I have 3 times I times the square root of 2. This is kind of the convention. I really like to write my numbers like this, where I have the real coefficient, right, 3 out front, and then I after the number, and then the square root last, just so that it's really easy to see that this stuff is outside of the square root. Versus if we put it on this side, a lot of times it kind of looks like it could be underneath the square root. This isn't the only correct way to write this, but it's kind of easier to read. So this is our answer here. Again, when we're doing stuff like this, we want to use these factors that are perfect squares. So again, we're looking for perfect square factors. What are perfect squares? Well, anything squared, right? So 4, 9, 16, 25, 36, 49, 64, etc. These are all perfect squares. So we want to look for when these are factors of a number that's under the square root. So, for example, let's say we were looking at 6 times the square root of negative 80. First of all, before we do anything else, we want to pull out the I. So we have 6I times the square root of 80. Now, how can I reduce this or simplify this square root? Well, we want to look for one of these factors. 4 is certainly something that divides 80. We could start with 4 if we wanted. Let's go ahead and do that. So we have 6I times, if I pull 4 out here, I get 20 left over, right? 80 is 4 times 20. I can split those up. Square root of 4 becomes 2. Now I have 2 times 6 times I, so I can rewrite that as 12I times the square root of 20. Is this the answer? Are we done? Have we simplified all the way? Not quite, right? This square root of 20 can also be reduced. So remember, we want to look for perfect squares. 4 also is a factor of 20. So I can do the same thing again. So I have 12I times the square root of 4 times 5, right? 5 is what's left over. I can split up again. Again, square root of 4 is 2. I have 2 times 12 times I, so I have 24I times the square root of 5. Now this is my answer. 5 cannot be simplified anymore. Let's say I had the square root of -8 times the square root of -6. First things first, I have to take the i's out first. So I have I times the square root of 8 times I times the square root of 6. I can combine like terms here. So I multiply the I times the I, so I have our I squared. Then I definitely have 8 and 6 underneath the square root as well, right? If we can split a square root up, we can also combine it if they're being multiplied together. I squared is going to become -1. So I have negative square root of 48. Are there any perfect square factors of 48? Yeah, there are actually a couple. We can see that 4 is also a perfect square factor of this number, but so is 16. 16 was actually also a perfect square factor up here, but let's look at this one now. So we have negative 48, which can be split into 16 and 3. We can split those up. We get negative square root of 16 times the square root of 3. Square root of 16 is just 4. So my answer is -4 square roots of 3. We could have also, there's an alternative way of solving this. Once we got to this point where we had -1 times the square root of 8 times 6. Clearly we could have looked at this and said, oh, I know that the fact that 4 is a factor of 8. So I can change this to look like negative square root of, if we could split this, we could split that 8 up. So we'd have 4 times 2 times 6. We split that 4 off. We have negative square root of 4 times the square root of, we have 2 times 6 left over. We can just multiply that out if we want. We have 12. So 4 becomes, square root of 4 becomes 2. So we have -2 times the square root of 12. Can we reduce the square root of 12? We totally can, right? 4 is a factor of 12. So we can do the same thing kind of over again. So we have 4 times 3, we split off the 4. The square root of 4 is 2, so we have negative 2 times 2, which is 4, times the square root of 3. So we have negative 4 square root of 3. Again, same answer. So this is an alternate solution for this problem. We can also do more sort of algebraic stuff with this as well. Let's go back to the lab manual, the page following the page we were just looking at. Let's look at this first question. So we have negatives under the square root, so we definitely need to pull out the i's first. So we have 2 plus I times the square root of 6 times 5 minus I times the square root of 6. Can I simplify 6 at all? I cannot, so let's just keep moving. I have 2 factors with 2 terms each, so I need to FOIL here. So I multiply first terms, I get 10. I multiply outside terms, I get negative 2i times the square root of 6. I multiply inside terms, I get 5i times the square root of 6. And then I multiply my 2 last terms, and I ran out of room here. Let's see if I can kind of write it. I have a negative I squared times the square root of 6 squared. So we have a fair amount of simplifying to do here. So I have 10 minus 2i square roots of 6 plus 5i square roots of 6. If I think of I square root of 6 as sort of a unit, if I have negative 2 times something, right, negative 2 of something, and I have 5 of something, how many somethings do I have? 3, right? Negative 2 plus 5. So if I have negative 2i square roots of 6 plus 5i square root of 6, then I have 3i square root of 6. Last but not least, I have minus I squared. I squared is, of course, negative 1. And then the square root of 6 squared, hopefully at this point we're getting kind of used to this, is going to be just 6. So I have negative 1 times 6, or positive 6. So my final answer here is 16, right? 10 plus 6 plus 3i square roots of 6. Awesome. Let's do this one here. So first things first, I need to pull out the i's. So I have 5 plus I times the square root of 7. And then 5 minus I times the square root of 7. Again, I need to FOIL. So I multiply these first terms, I get 25. Outside terms, I have 5 times negative 1, so negative 5 times I times the square root of 7. Inside term, I have plus 5. Okay, y'all, unfortunately, my camera shut off again because my phone ran out of storage. So I missed the end of this problem. So let me walk us through it. I believe we were writing things out here, foiling, right? We had our first term, outside, inside, last. Our outside and inside terms, right, are negative and positive of the same number. So they are going to cancel because adding them together is going to become 0. Then I squared becomes negative 1. Square root of 7 squared becomes just 7. So we're left with 25 minus negative 7, so plus 7. We end up with 32. So we have a real number for the answer here. We've had this before, we've seen this before, right? There were a couple of questions earlier where we had real numbers from non-real complex numbers being multiplied together. Let's see what's going on here. Let's go back to our notes really quickly for a definition. The complex conjugate of A plus BI is A minus BI. Simple as that. So, for example, if we were looking at 2 minus 2 plus 3i, what is the conjugate of this? We have 2 plus 3i, so our conjugate will be 2 minus 3i. If I wanted to find the conjugate of 2 minus 3i, what would that be? Well, we're flipping the sign of the imaginary part, right? We've flipped the sign of the imaginary part here. So if I wanted to find the conjugate of 2 minus 3i, I would need to flip the sign back to positive. So the conjugate of the conjugate is our original number, right? It works both ways. Okay, second one, let's say we had 3 minus 7i. Well, if I find the conjugate of this, what is that? We flip the sign of the imaginary part, so I have 3 plus 7i, and vice versa. Last but not least, what if I had the imaginary number negative 4i? Well, remember, the conjugate is flipping the imaginary part. So the sign of the imaginary part here is negative. We need to make it positive, so we have positive 4i, and vice versa. So what's important about this? What's important about conjugates? Well, let's say I multiply a complex number by its conjugate. I need to FOIL here. I have a squared minus abi plus abi minus, there's two b terms, so b squared, and there's two I terms, so I squared. If I simplify, I have minus abi and plus abi. When I add these together, they become 0, so this cancels with this. I squared becomes negative 1, so I'm left with a squared minus negative b squared, so plus b squared. What's interesting about this? Are there any i's here? No, there are no i's. So this is a real number. So what's important about conjugates? Well, multiplying a complex number by its conjugate gives us a real number. We've seen this a few times before, right? We just saw this in the lab manual, right? When we pulled out the i's here, we have a real part of 5, an imaginary part of plus square root of 7, right, times I, and then real part of 5, and then minus square root of 7 times I. So these two numbers are conjugates, right? These are conjugates. And we got a real number. We've seen something similar to this before, right? We've seen a squared minus b squared a few times, right? So I have two sort of important facts. If I have a plus b, right, regular old a plus b, times a minus b, this gives me a squared minus b squared, right? Because similarly, the outside is going to give me negative ab, and the inside is going to give me positive ab, and so those middle terms, those inner terms, will cancel each other out. This is what we call a difference of squares. If you're feeling like you don't super remember the difference of squares, we've seen the difference of squares before when we have something like x squared minus 16. The difference of squares tells us that this is equal to x plus 4 times x minus 4, right? And it's because if I were to solve for the roots of this, I could bring the 16 over. I would have x squared equals positive 16. I would take the square root of both sides, and I would get x equals positive and negative 4. If I have the root positive and negative 4, it means I have the factors x plus 4 and x minus 4. So we have this fact, right? So we've seen difference of squares before. What we've just talked about, a minus bi, a plus bi times a minus bi gives us a squared plus b squared. This is the sum of squares, right? This is two squares and then the difference between the two. This is two squares and the sum of the two. If I have a sum of squares, then we still have this a plus b, a minus b type structure, but b is multiplied by I in both factors. If we have a squared plus b squared, it's going to end up like this. Another way that we can sort of think about this is in terms of the difference of squares. So let's say that we are looking at a plus bi times a minus bi. In this case, I have a plus something, right? Let's make bi kind of a unit, and then a minus something. This is the same structure as the difference of squares. And what difference of squares tells us is that this is equal to, right, a squared minus whatever my second thing was, squared. My second thing here was our unit, bi. So bi squared. If I simplify this, I end up with a squared minus b squared I squared. I squared is negative 1, so I have a squared minus negative b squared or plus b squared. So with this, we can either sort of remember this fact that multiplying them together is going to give us the real part squared plus the imaginary part squared, or we can think about each of these situations individually as a difference of squares situation that ends up giving us a squared plus b squared. If that didn't make sense, don't worry about it. But if it did help and make sense, that's a great way to think about it. Okay, let's look at a couple of examples. Let's say you were asked to multiply 4 minus 5i by its conjugate. So first of all, what is the conjugate of 4 minus 5i? Again, we flip the sign of the imaginary part. So we have 4 plus 5i. We multiply first terms, we have 16. Outside, we have 4 times 5i, or 20i. Inside, we have negative 5i times 4, or negative 20i. And then our last term is negative 5 squared, or 25i squared. These guys will cancel, right? We have the plus and minus. I squared becomes negative 1. So our answer is 16 plus 25, which gives us 41. Now, in order to get here, we had to do this process, which we kind of already did, right, when we were figuring out the fact from before, right? Remember, our fact tells us that if I multiply two conjugates together, I get a squared plus b squared. A here is 4, and b is 5, or negative 5, doesn't matter. A squared plus b squared is 4 squared plus 5 squared, which is 16, plus 25, which is 41. So we could have solved it this way. Might have been a little bit quicker. Definitely would have taken a lot less work, and we would have gotten the same answer. Let's say we were doing the same thing with 2 plus 3i and 2 minus 3i. Let's use sort of the difference of squares method here. So we have 2 plus something times 2 minus that same thing. So our difference of squares method tells us that this is actually equal to 2 squared minus this, right? Whatever the sign is flipped on, squared. So 3i squared. Okay, so this is again using difference of squares. 2 squared is 4, and then minus 3 squared times I squared. 3 squared is 9. I squared is negative 1. So I have 4 plus 9, or 13. All right. I know that was a long lesson. Welcome to complex numbers. We're going to see them, honestly, for the rest of the semester. So hopefully this is feeling okay. Thanks, y'all.